So let's go back and do a real brief overview. So we're looking at diode gauge, right? Which I'm not really sure it covers too well in your textbook, but it should. So what is on the left? So this guy's new logic. Okay, how do you know it's an AND? Because if I have any of these inputs over here are low, that low is going to come through, right? You understand? So I got to have all highs over here to get a high out. Good, Maurice. And of course, this is a watt. This on the right is a watt. This is an OR. This is an AND. This is an OR. Okay. You understand? And what we did the other day is we set up a thing called a truth table. What's a truth table? Well, what it shows you the output for all given inputs. And this is binary, folks. So how many inputs would this guy here have? How many possible input combinations would it have? Well, all I have to do is look at the number of inputs and raise 2 to that power. So I'd say 2 to the third means this guy here should have 8 combinations. That makes sense? And then, of course, then I would just come up here and start counting. 0, 1, 2, 3, 4, 5, 6, and 7. And that's it. Now look, 1, 2, 3, 4, 5, 6, 7, 8. That's the total number of combinations you could possibly put on it. Just count the number of inputs, and this is for any gate. By the way, we call these gates, by the way, because you can see how it got the name gate is that basically, if I've got all ones over here, it lets the cows go through. So basically, it's opening up the gate. If any of these things go low over here, then the gate would be closed, and that's how it got the name, right? You understand? So we say, okay, only one combination would open the gate. Would let the high inputs get through and make a high output, right? Now on this one, this is an OR gate. So see, I got the name a gate because if I put any high over here, the output goes high, which is pretty interesting. And then what we would do is we would literally come over here and split this into, normally we give the inputs a name. And when you look at schematics, they are going to be given a name, which we refer to as, they call them mnemonics. A mnemonic is a memory jogger. So over here, I would write A, B, C. In a car, it might say, you know, like B, P, or B pressure, or something like that. Understand? So that way, you get a feeling of what that input's coming from, maybe brake pressure or something like that. Usually it's a mnemonic, so it's usually an abbreviation. So it might be like, you know, BPRL for left brake pressure. So this would be what we call a mnemonic. So we'll look at some true schematics. So we're going to look at some true schematics. The old book used to have one in the back. I don't know if this newer book still has it or not. Look at that. Yeah, so there's all the way back on the 934, 935. If you take a quick glance back there, what you're actually looking at, this is a digital schematic on 934. You don't have your book, you need to kind of look at somebody that's got it. But look, the inputs and the outputs have names. Y'all see that? And we call these mnemonics. In class, we're going to call them maybe A, B, and C. But on a schematic, they're going to be given a name, and that name would mean something to a technician that came up here and worked with it. So y'all see that? So, but these are gates and these are symbols, and we'll come up and look at this. And we're going to look at those diagrams several times when we get in and start talking about these different logic gates. So normally we put inputs on the left and we put outputs on the right. Instead of putting true, false, or anything like that, we put ones and zeros in a function table. But we'll look at some that's got H and L's. So we'll look at some of the data sheet. Usually in the data sheet for the gate, it gives you a function table on if it's at all possible. But you got to understand these things are okay until you get, if you got 5 inputs and there'd be 32 combinations in your truth table. You know, just adding 1 input, we increase by a power of 2. So we'll be looking at gates that's got, you know, our circuits. When we get into combinational logic circuits, we'll be looking at them that might have 10 inputs. Well, 10 inputs means I would have 1,024 combinations in my truth table. So truth tables are pretty good for basic gates because it proves to us that you know what it's going to do, but we're not going to deal with truth tables when we get into some of these gates that have a lot of inputs. Does that make sense? So this guy right here is an AND, so it would have a truth table that looked like this. So a truth table, what's on this side? On this side is going to be inputs, and on this side it's going to be what? Output. And an OR gate requires at least 2 inputs. You can't use the term any if you only got 1 input, right? You'll understand that. And an AND gate requires at least 2 inputs, but how many inputs could they have? Well, I could come up here and drop down and do this, and now I have a 4 input AND gate, right? And now my truth table has jumped to 16 inputs, so now it'd be cumbersome. Even in PLCs, you're going to learn a technique called Karnoff maps, which you use to reduce, and it's covered in the book. It's not one of the things I like to use, so I usually don't teach Karnoff maps. I like the math. We have a math called Boolean algebra. And if you're good at math, you can reduce the circuit in no time. Are we okay? So this is a what? This is a AND. This is a OR. And we're starting into BJTs, bipolar junction transistors. So when you hear the term transistors, it's kind of misleading because we have 2 types of transistors. Actually, we have more than that. We have BJTs, which are bipolar junction transistors, which is what's going to be in the logic that we're using. And then we have FETs, which are field effect transistors. And we have several categories of this. We have JFETs, which are junction field effect transistors. We have MOSFETs, which is the predominant logic over here now. And then we have 2 versions of this. We have DMOSFETs and we have EMOSFETs. And we'll get a little feel of this later on when we get into a type of technology called CMOS. I don't know if y'all heard of CMOS, but usually it's going to be one of these categories over here. So in digital, you're going to run into the logic that we're dealing with. There's 2 types of logic that use bipolar transistors. One of them's called TTL, and one of them's called ECL. Just about all your other logic out there is this guy right here, or combinations. We have something called a EGBJT, which is becoming very popular in variable speed AC drives, which stands for insulated K bipolar junction transistor. And what they've done is they've combined one of these and one of these into one unit. And of course to you it looks like a transistor, but it's actually an insulated gate BJT. So you can see when we use the term transistors, people use that, you probably heard that term a lot. We just can't say transistors because there's all kinds of devices that are considered to be transistors. The ones we're looking at are transistors, and this is used in the logic that we're going to predominantly study this semester, and that's going to be what we call transistor logic. And transistor logic uses bipolar junction transistors, BJTs. And in your textbook, does a pretty good job of covering this. we're not going to learn what makes it work on the inside. So if you look at page 46 in the textbook, then if you look at figure 4-27, this is the actual makeup of a bipolar junction transistor, which to us right now really don't mean anything. And it shouldn't. Now when you get into, so an NPN looks like this. And this is the predominant transistor that's used in bipolar, in TTL, so we'll spend a lot of time with this guy. So an NPN transistor means what they do is they have material here. It's not negative, but it reacts to a negative charge. And this tells us how we bias it. Did we talk about bias? I think we went over that. What is bias? Did we talk about that in this class? I'm doing solid state too, and this class is kind of overlap. I think Joe was in that class. This is a DC voltage. Applied to a semiconductor. Now, when we talk about semiconductors are silicon and germanium. If you just took a chunk of silicon, it is a semiconductor, which means it's neither a conductor or an insulator. It's right down the center. It acts like a resistor. Well, so this is not pure silicon. What they do is they introduce impurities into these things deliberately, and then we can control the conduction characteristics. So this is not a pure semiconductor. It has been what we call that doping. And you'll learn about that when you take solid state, how these N materials and P materials are already made. We call this a semiconductor, but in true life it should be called a doped semiconductor, because this is not pure silicon. This has been modified so we can control the conduction characteristics. So we can actually literally control the amount of opposition this thing says. So we come over here and we say applied to a semiconductor. It would probably be more precisely to put a solid state bias. That controls its operating conditions or parameters. I'm running out of room on mine. Sorry. I keep getting those PER parameters. Get those messed up all. But anyway, so what we have to do, we have two techniques we can control this thing. We got three regions, and we talked about the three regions. Anybody remember what those are? So we can operate them in cutoff. Yeah, cutoff, it acts like a closed switch. Then we get activated in what we call the active region. Here it acts like a rheostat. What's a rheostat? What's a rheostat? Y'all know what a rheostat is? Rheostat is a variable resistor. The symbol, a variable resistor. So this is a symbol for a resistor. Y'all all had DC, right? DC is the primary. Y'all did go over the rheostats. Anytime we put an arrow through a symbol, it means it's variable. So rheostat is going to have a knob on it, or it's going to have a slider. It's going to have something on there that you turn, and it controls the amount of R. So that means if I had like a 10K rheostat, it means I could set that resistance anywhere from 0 to 10K. Huh? That's probably a potentiometer. A potentiometer is a little different in that this is a true variable resistor. A potentiometer has a different symbol. So in DC, you learn something about voltage dividers, right? You understand? Y'all remember voltage dividers? So in a voltage divider, I can come over here and I can have like 2 resistors. And if I come over here and put a DC voltage across it, and that's a crummy symbol for a DC voltage, guys. Let's turn it this way. So that's the symbol for a DC source, right? Yeah. And let's say this is 12 volts. And let's say I set this, these are 10K resistors, and I set this, no they're not, these are any size resistors. Let's say I set this to 4K, and I set this to 1K, but what I'm going to do is I'm going to take my meter, which is a real high resistance, and I'm going to put it right there. Well, this guy right here would drop 4/5 of the voltage. This guy down here would drop 1/5. Okay? We have so how much voltage would be across the 10K? Well, I'd say, y'all know what we call, did they teach y'all the voltage divider formula? Yeah, that's a neat formula because you don't have to solve for current. And most of the time when you're dealing with 2 resistors, you can calculate RT in your head. Okay. Well, the voltage divider is just that, and that's what a pot is. A pot is a variable voltage divider. So that means if I have a 10K pot, and this is 1 and this is 3, the resistance between 1 and 3 never changes. So if it's a 10K pot, if I measure between 1 and 3 out of circuit, it will always measure 1K. So what you're doing with the pot is you're doing this. So right now, if we call this R1 and we call this R2, then R1 is going to be, R1 would drop 4K over 5K. So K is going to cancel, right? You understand that? And then we'd multiply that times 12. And then that would give me voltage drop across R1. So voltage drop across R2, since it's 1K, is going to be 1K over 5K. So what you do, the voltage divider formula, you can calculate the voltage drop in a series circuit without calculating current. Because the resistor will drop a voltage relative to the other resistors in the circuit. And that ratio will always be the same, which is neat. So if you've got a circuit that you're putting different voltages on, and you're constantly recalculating I, so you can use Ohm's law, right? V is equal to I times R, then you'd have to do to every voltage. But this guy here would always drop 1/5. This guy right here would always drop 4/5. And if I knew that, I could put any voltage on there, and I could calculate the different voltage drops just like that, because all I have to do is multiply it times the ratio. So the voltage divider formula is Rx is equal to R. I'm sorry. Yeah, I gave you. I'm doing it wrong. So VRX is what I should put, is equal to RX over, yeah, times your social. That's the voltage divider. It's real neat. When you get into solid state, this is the guy we use. When we're trying to calculate the bias on these semiconductors, we use this guy right here. So that means then I'd multiply this times 12. That makes sense? Okay, and what would we get here? 9.6, and what do we get down here? Of course, you could use Kirchhoff's law to calculate that, right? Okay, 2.4. Well, notice these are always equal to 5K. Well, what if I maintain 5K for RT, and then I come up here, and then I come up here, and then I change it? And this is what we're doing with a pot. So 5K. So I could make this 3K and I could make this 2K. Now what just happened is the ratio changed. So my meter would read a different voltage. Well, what we're doing with a pot is if we got 10K, basically I've got two resistors in there, right, you understand, that's splitting between 10K. But what's nice here though, if I adjust it all the way up, then I get the applied voltage. If I adjust it all the way down, we usually get 0. So normally with a pot, I can get any voltage on the output between my applied voltage and 0 volts. So a pot, we use a pot to control a voltage. We use a rheostat to control a current. Yeah, so it's a variable voltage pot. That's exactly what it is. These are fixed voltage dividers. These are variable voltage dividers. We run into a situation in solid state where we're trying to set up an input signal, and they say that we need to put 1 volt in to get 10 millivolts out, and they set up a fixed voltage divider to get 10 millivolts out. Our generators won't put out 1 volt. And every one of them put out something a little different. So if we use a fixed voltage divider, we'd never get 10 millivolts. So what do we use? We use pot. And now it's up to me to decide. Now I can put my meter on the output, right, you understand, and do what? I can get the exact voltage I need. So what we're doing is if I come over here and use a bipolar transistor and I use it in an active region, we come up with this circuit right here. So the transistor acts like a rheostat, but we're controlling the rheostat electronically. So that means if I take my output across the transistor, then I can vary it anything I want to. So if the input is coming over here doing this, then the output can do this. It's going to be a mirror image, but it's going to have gain. Because the voltage over here is going to be almost nothing. The voltage over here might be 100 volts, right? You understand, on the rheostat side. So this is operating in the active region. In this class, we're not going to use the active region because this is digital. And what is digital? Digital is ones and zeros, off and on. So what we're going to do in this class is we're going to operate it between cutoff and what we call saturation. So when we do saturation, it acts like a close switch. So we can hook that switch different ways. So I'm going to come up here and erase this. I didn't want to do that, guys. I don't want to do that. Where's my blank? All right. So we got two places we're going to use this switch. We can use it like this. So I could put my load right here. That could be anything. Could be a light bulb, could be an LED, could be a relay, could be anything. I'm going to come over here and put my switch right here. Let's don't draw it as a transistor right now. Let's draw it as a switch. Single pole, single throw switch. Down here we have common. So instead of using that, let's use a light bulb, because the light bulb is sometimes a little easier to see because we get a visual indication of when the switch is closed. You can't have one without the other. So what we're going to do in digital is we're going to switch these transistors between cutoff and saturation. So it's just like this switch. What if I couldn't cut this switch off? What good would it do? What if I couldn't close the switch? What good would it do? It wouldn't do me any good. Right? You understand? If I couldn't cut it off, then I'd use a straight piece of wire. right? I'm sorry. If I couldn't open it, I'd use a straight piece of wire. So right now, the transistor is operating in cutoff. So it's acting like an open switch. What would the light bulb be doing? Would it be on or would it be off? Huh? What do you mean what wrote up? What? Yeah, I got it written wrong. I got it up there twice. So, thanks. I was just doing that to see if y'all was paying attention. I can understand why you're getting confused now. Yeah. So cutoff, it acts like a what? Open switch. So we're operating in cutoff, right? I'll do the symbol right. So you got to give me half credit, right? Okay. So is the light on or off? It's off, right? You'll understand that. There's no complete path for current flow. Okay. So if I come over here and close the switch, this would be active. This would be, we're operating the transistor in saturation, and now it acts like a closed switch and the light will come on. So this is one way we can operate it as a switch. So you see this all the time. You know, you go in there and touch a little button and your computer comes on. That little old button is not turning the computer on. It's probably saturating a transistor switch somewhere so you can get a bunch of current gain, right? You understand that? Sure. And on this computer right here, of course there's a little more to it, but I guarantee you there's a transistor inside an IC somewhere doing this for us. The other way we can connect the load, which is the way we're going to have to look at, because this is the way TTL logic works, is we're going to put a resistor up here, a fixed resistor right there, and it is a resistor. And then I'm going to come out here and I'm going to put a switch. That's my transistor. And I'm going to come over here and let's say we put plus 12 volts. And then I'm going to come over here and I'm going to put my light bulb over here. Of course, now it's going to be less than plus 12 volts. It would have to be like 5 volts. We'd have to size these things. So right now the transistor is cut off. Would the light be on or would it be off? Is there a complete circuit? Sure, there's a complete circuit. I mean, I can come up here, I can see that. I mean, here it comes right up through here. Here's a path. Is there a path between here and there? Sure, here it comes right there. So it comes up, goes over here, goes to that resistor there, about 12 volts. The light bulb would be on. Yeah. So when the transistor is cut off, the light is on. Okay, so let's come over here and erase some of this and close the switch. And this is what gets some people confused. Is the light bulb on or off? It's off. There's no difference in potential. You don't get any work unless you get a difference of potential, right? You understand? So how much? What we have no difference in potential across a straight piece of wire. Now, of course, now this resistor is going to drop all the voltage. A while ago, it was dropping 7 volts, but as soon as that switch closed, this guy's going to drop all 12 volts because this bottom is connected to common. There is no difference in potential across the light bulb. It will not light. So here, on this one, if the switch is open, the bulb is on. If the switch is off, the bulb is off. If the switch is closed, the bulb is off. And this is the way TTL gates work, by the way. They actually put the load outside. So this is a real popular way. Now, if we came over here and did this with a transistor, that transistor, we can hook the load in 3 different places. So this is a symbol for a NPN, not pointing in. The big thing is these 2 guys right here, P, positive, N, less positive. It's not going to be negative. It's going to be less positive, right? You understand? Right here it's going to be 0. And then this gets kind of confusing. This is an N up there. Well, what we do is we have to forward bias this junction. So forward bias means we put a positive on the P and we put a less positive on the N, right? You understand? And what we have to do is we have to reverse bias this junction for reasons we're not going to talk about. So that means even though this is N, we point it toward P, the positive. And this is the way you forward bias an NPN transistor. A PNP, we would do everything the same. But it's a PNP. Okay, y'all understand? So here, we would run this guy here off a negative supply. And then the base would be less negative, and then this would be positive with respect to that. That makes sense? Go ahead. To go then. I mean, what am I making? So this is pointing in, right? This is what? Not pointing in. So we're going to be yeah, why? So not pointing NP, not pointing P. Not pointing in. This makes sense. This is pointing in, and that right there you just learned. So normally a PNP transistor operates off a negative supply. An NPN operates off a positive supply. Now there are some exceptions to the rules, but we're not going to get into that. Because it's hard enough already. So what I got to do is I got to make the base positive. Now what we got to do is we got to turn this thing on. We got to make the base approximately 7/10. So here's the leads. We looked at that the other night, right? We call this lead down here. Y'all remember? This lead is referred to as the emitter. This lead right here is referred to as the collector. Now you need to know that because that's what they call them in the data sheet. So when they show you, they show you that where the emitter, they don't say PNPN. Somewhere in the data sheets it's going to say NPN, but they're going when they give you the pin numbers, they're going to call them the emitter, the collector, and this guy right here is called the base. So the base is the control. That's like the valve. It's not the valve, it's like the control for the valve. So on your sink, it would be the knob, right? You understand? Your washing machine, it would be a solenoid back there. That's actually controlling. So I've got to make this P. So we got two options. So we got to make sure this guy right here is at least 7/10 of a volt more positive than the emitter for silicon, and that's all we're doing. But I could literally come up here, so I'm going to have to put a voltage over here this more. So let's say I put plus 5 volts. Well, that means I'm going to have to size a resistor to drop 4.3 volts. Because Kirchhoff's law says the sums of the voltage drops in a loop has to equal to the applied. This makes sense so far? So that means if I come over here and put plus 5 on there, then that creates a circuit, and then what we do is we come up here and generate a path through here. Now basically the way this thing is set up is that the emitter is the base is a little tiny thing. And up here I've got plus 12 volts. Right here I've got plus 5 volts or 7/10. So what happens is that when these electrons start flowing up and going this way, 99.9% gets into that little old thin base and sees that big old plus 12 volts up there sucking up there. And what it'll do is 90% of the current, probably 99%, goes that way. If I come up here and put this to 0, then this right here, stops. Now it cuts that guy right there off. So we have to have a current in the base before we get a current through the valve. So the current through the base is controlling the current in through the valve. So what we have on the transistor, we have a rating. Most folks call it the beta. So they call it the beta, and they abbreviate it, of course, with the symbol for beta. But your data sheets are going to call it H of FE, which is the forward transfer. We call them the hybrid parameters, but it means exactly the same thing. What it means is the hybrid parameters for a forward bias transistor with the emitter common. You can see here the emitter is what? Common. That's what H of FE is, which is the beta. Now what the beta is calculated by taking the collector current and dividing it by the base current. And this is where we get a transistor is a current valve. It's just like a water valve. Y'all understand that? A water valve controls the flow of water. Well, a transistor controls the flow of current. So if I'm going to get a voltage out of a transistor, by George, I'm going to have to run it through a resistor. So if I measured if I didn't put that resistor up there and I turned this thing on and I closed the valve, I got a short circuit and it burned my transistor. If I was operating in the active region, I could control that current precisely, but I would never see a voltage because, you know, I could come over here and I can put a resistor right here, and I can put a battery right there, and how much voltage would that resistor drop? Come on, guys, how much voltage would that resistor drop? Huh? They say none. I mean, in Kirchhoff's law says the sums of the voltage drops in a closed circuit has to equal to the applied voltage. So whatever voltage was on this battery would be dropped across that resistor. What if it's 12 volts? Well, that resistor would drop 12 volts. What if it's 30 volts? Well, that resistor would drop 30 volts. Well, what if it was... So if I wanted to get a voltage out beside the applied voltage, I'm going to have to set up a voltage divider, right? You understand? So the only reason this right here would mean something right here if I have that resistor right there. So now if I close the switch, the voltage over here is either going to be this, or it's either going to be 5 volts. If I put a resistor over there, it's going to be a voltage divider, right? You understand that? Yes or no? So the only way you're going to get a voltage out of a transistor is if you put a series resistor in there. So you put a fixed series resistor, right? You'll understand that. So this is why it's pretty dangerous to run your power amps unloaded, by the way. And you can blow them suckers up because you've lost the resistor. And you get what we call reflective power. So if you got a 100-watt amplifier and you unload it, the 100 watts is going to be reflected back into the amp. And it'll blow what we call your outputs. So if you got a big power amp in your car and it kicks off one time because it's got an overload, don't come out there and keep resetting it because you'll blow the outputs on your $500–600 power amp. Might even burn your speakers up because it's putting DC on them now instead of AC. So that means if I'm over here, so our collector current will always be greater than our base current. So if I've got, you know, let's say 100 milliamps out. Now the emitter current, it supports two things. It supports the base current and it also supports the collector current. But it might take, if it's got a beta of 100, then it would take 1 milliamp of base current to get 100 milliamps worth of collector current. But we're actually not going to get 100 milliamps. We're going to get 99 milliamps up here. But notice, for all practical purposes, we're going to assume that the collector current and the base current, the emitter current and the base current are equal. It just gets too complicated because they're practically equal to each other. So for all practical purpose, we're going to assume that IE is equal to, this is actually true, right? Approximately equal. We all understand that? But in here, we're going to assume it's what? They're equal. So if I could measure the collector current and measure the base current, then I would say, okay, the beta is equal to 100 milliout divided by 1 million. The milli is going to cancel, so the beta would be 100, and that is no unit. So it is a gain, right? So a gain has no unit. It's a multiplier. So, you know, you say your employer says, I'm going to give you a 3% raise. You say, oh, great, I'm going to get a $3 raise, because that, what you would do is you would take what you're making now and multiply it by 3%. So gains have no unit. Sometimes we use a unit called decibels. Have you ever heard of that? But it's similar. Decibels is similar to milli, micro, and nano. What decibels does, it gives us a way of representing extremely large numbers and extremely small numbers with a small number of digits. So you ever heard of dB? dB? If you're in audio, I guarantee you've heard of dB. It's decibels. It was originally brought out by the human ear. Your ears are not linear. Y'all understand that? Your ears are logarithmic. It's actually unlinear, and they figured out that when they raised the power to the output of the amplifier, how much power did it actually take for the human ear to hear a doubling of power? And it takes a lot for you to hear a doubling in volume. Takes a lot of power, a lot more than doubling the power. So if I double the power to my output, your ears would not hear a doubling in power. It runs in logs, tens. So basically, it has increased by 1 dB, which is 1 dB would be 0.01. And from that, though, we've moved that into all different types of, all different types. So originally, the dB was brought out about by sound power, but now we use it all the time because it just sounds good. I got a 10 dB gain. Wow, what's it got? I have no idea what you're talking about. I don't know if we get into dB in this class or not. But anytime you get into gains, a lot of your gains are given in decibels. Anybody know what a dB is? Anybody know what a dB is? It's actually logs. Natural, it's a common log. Is what it is. Y'all know what a log is? You take a log and remember what it is. Oh, anybody know what that is? Log is this right here. That's a log. So we can represent any number raised in 10 to some power. So if you had a log of 2, that means that would be 10. That'd be 100. Well, over time, this exponent became known as a bell. So we'd say 2 bells. And then they needed a way to round, so they would take the bells and multiply it by 10, and this is that became known as a decibel. So 2 bells would be 20 dB. 3 bells would be 30 dB. But if I wanted the actual number, I would just in my head move it to the left and then raise 10 to that power. So if you find the 10 to the X key on your scientific calculator, it's probably the same key as the log key. You just have to hit shift, but it's in there somewhere. So what we would do is, what would happen is if I put a 0 right there, now we don't mean to nothing. In this situation we would, but then my output would cut off and I'd have no current flow through that resistor, right? You understand? But what if I came over here and put my meter, or took my output? Everybody okay? We're going to get rid of a lot of this stuff. And I took my output and I put a voltmeter right there. Okay, everybody okay so far? Alright, now I come over here and I put +5 over here. What would the voltmeter show? Let's say this is 12 volts. What would it read? It's either going to read 12 volts or it's going to read 0. By the way, transistors can never, I didn't say they are a closed switch, I say they what? Act like a closed switch. When a transistor saturates, it will drop a voltage because it is not a closed switch. It's got material in there. And we'll look at that. They call it the saturation voltage. Usually it's going to be less than 1 volt. So that's usually the way we determine if it's saturated. We can measure across the transistor. If it's less than 1 volt, we say it's saturated. If it's equal to this, we say it's cut off. So that voltage collector to emitter is a very important measurement to determine what mode the transistor is operating. So if I put 5 volts on there, are we going to have base current? Yes. Transistor is going to saturate. It's going to act like a closed switch, right? To understand what's the meter going to show. This is what you got to do, and this is a problem. People want, and I understand what's going on, and I undoubtedly I just don't know how to teach it. So I've got a resistor right here, and I've got a transistor that's acting like a switch. And I've got plus 12 volts. Y'all understand, to get current to flow through anything, you have to have a difference of potential. Okay. So what I just did with that 5 volts is I came in here and I closed this switch. And I'm taking my voltage measurement right here. So what I've done is I've connected the top of the light and the bottom of the light at exactly the same potential. Now that could be 5 volts and 5 volts. Here we're using common. So if I have 5 volts on one side of a resistor and a 5 volts on the other side of the resistor, how many volts is it dropping? It's dropping 0 volts, right? You understand? And we do that too, by the way. So what would my meter measure? Well, my meter is going to measure approximately 0 volts. It's not going to be 0 volts. Over here it would measure 0 volts. Over here we're going to say approximately 0 volts. Because it's not a closed switch, it's a transistor. So if we say this is a 1 and we say this is a 0, that means how many inputs can I put on, how many different combinations can I put on this input? I've only got one input, folks. How many combinations? Well, let's see, 2 to the first. I've only got one input. So how many combinations can I put on it? 2. I can either put a 0 on there, or I could put a 1. So right now I'm putting a 1, so I put a 1 in. What did I get out? 0 out. Okay. So we put a 0 in, transistor would cut off. Okay. We would come over here, that would be like me doing what? Opening the switch. Now what would my meter show me? Well, your meter has about 10 to 20 megohms worth of resistance, so it's going to show me 12 volts. So this is going to go up to 12 volts. So here I put a 0 in, right? And I got a watt out. 1 out. We just did logic. This is a unit, this is a circuit we call an inverter. and the logic is called a NOT. So the circuit has a name. We use this name so much. So an inverter, y'all see why it's called an inverter? Because it inverts the input. But the logic is called a NOT. So we have ANDs, we have ORs, and we have NOTs. And then we got two more, and we know all the 5 basic gates. Yeah, well over here, this simulates cutoff. Okay, so when I put a 0 here, the transistor cuts off. When the transistor cuts off, it acts like an open switch. And in a series circuit, the entire voltage is dropped across the opening of the circuit, right? You understand? Here, what's the opening of the circuit? Well, the transistor is. So the entire voltage is dropped across that. So if I put a 1 in, I get a 0 out. If I put a 0 in, I get a 1 out. This is an inverter. Now, what's going to happen if I take my diode AND gate and I feed it into an inverter? Well, we'll talk about that after the break. So let's take a break. Physical size of a vial. Yeah, how much water's got to let flow through it, right? So the more flow it's got to control, the bigger it's got to be. The less fluid it's got to control, the smaller it's going to be, right? And of course, if I'm a plumber, I'm going to choose the right valve. If I choose a valve that's too big, it would probably work, but it's just like if I use piping that's too big, I would end up costing me a lot more money, because the bigger the pipes are, the more they're going to cost, right? So choosing the right current valve. These guys come in all shapes and sizes. Basically, they're pretty easy. You can't say there's a lot of solid state devices that has 3 leads, but a bipolar transistor would definitely have 3 leads. So these are some bipolar transistors right here. Oh, let me unfreeze it. It's being recorded. Let me unfreeze it this way. So this is bipolar. I'll pass this tray around and you look at it. This is a bipolar transistor. This is the one we're going to use in the class. It'll focus in. So you can see there's quite a bit of difference in the physical size. And the biggest ones we have available is this guy right here. This is called a TO3 pack, and it's hard to see the 3 leads, but on this, the whole metal case is the collector. So this is the collector, and then these 2 leads right here would be, one of them would be the base and one would be the emitter. So whoever looks at them last, bring them back up here. This is an older motherboard. It's blown out on us. Power supplies on it blew out. But I don't know if you have seen it or not. This guy right here has 3 leads. You can see that little tiny thing right there, but focus in on it. That's a watt. That's a transistor. So the less current I have to control, the smaller we can make these things. And we get to a point where we're controlling, we're controlling 16 milliamps, then the size of the transistor can be extremely small. Then what they do is they take a piece of silicon and we call them integrated circuits. I know what that means. That's the way we abbreviate it. That don't mean what it means. What we do is we take a whole circuit and we put it on a single chip. These are called integrated circuits. Now these guys can't handle much current, but all they're doing is logic. All they're doing is 1s and 0s, right? You understand? And 1s and 0s don't require a bunch of current. Now if I come out and try to turn on something, then I'm going to have something bigger. But as long as I'm doing nothing but logic, then the size of the transistors can be extremely small. Which means if they're real small, we can get more of them on a single piece of silicon, which we call a chip, and that's what we call an IC. So a microprocessor, it doesn't use bipolar transistors, But most of your microprocessors now have over 1 million of these things on these transistors. They use ECTs, but still transistors. Because all they're dealing with is what? Ones and zeros, which is neat. By the way, this guy here, it's bad, so y'all don't have to worry about hurting the static electricity. Yeah, the power supply blew out on it. First we had a cap that blew up, and we replaced it, and it worked for a little while, then it blew again, and the whole power supply section burned out in it. But you can look at all these little 3-lead devices, especially up here in this corner right here, and these are all 3-lead surface mount transistors. That's all they are. This guy's got, we call them pins for a reason. These suckers right here will cut you. So be careful when you handle it, because if you let it slide across your hands, these guys right here can literally cut you. It's not going to be deep, but it's one of those kind of like a paper cut. You know, it's not deep, but it hurts like crap. You know. So this is an anti-static bag. Basically, it's got resistance, and these got the type of transistors. The big advantages of TTL is we can't hurt them with static. Bipolar transistors is you can't hurt them for static electricity, because static electricity can't generate a current, right? You understand? FETs work off of voltage. Static electricities can really generate a voltage. So FETs are susceptible to damage by static discharge. So when we get into CMOS, we'll show about some of the safeguards that we use to prevent us from getting static charge. So normally these things come packed in an anti-static bag. And then we have anti-static mats that we put the stuff on, and we can show y'all those. We put anti-static bands on our arm to work on these. And as long as you take just a few safety precautions, you're not going to bop them. And the problem is, usually when you bop them, they don't go bad instantly, but they will go bad. So it's kind of like, you get a nail in your tire. Usually it don't go flat instantly, but it will. It'll eventually what? It eventually will go flat. Of course, the police use those hollow nails, so they really flatten it. So I'll send this around. So normally we wouldn't handle this board directly with our hands, especially the bottom. You can handle it, but you'd handle it on the sides. As soon as you put it on the bottom, it don't mean you are going to damage, but you could easily. So we'll look at MOS technology later on in this class, and we'll look at some of the static guards that we go by just to prevent from damaging them. It's not that hard. I'll show y'all some of the equipment. It's not the static mats and the armbands are, the static armbands are like less than $5, and if you're going to work with these things, you probably need to get you some. I think on the ABB robot, when you open up the controller, they got a static armband in there already. So we're going to use these transistors we're using are called normally a transistor. And of course, this is a JEDEC, Joint Electronic Device Engineering Council. We call that JEDEC, which is an acronym. They allow you to register packages. And so what you do is you register a package. And then once that package is registered, then it becomes open technology. On transistors that's registered with JEDEC, since it has two what we call junctions in there, these transistors will always start off with a 2N number. If it's not JEDEC registered, it probably won't start with a 2N number. Yeah. JEDEC, Joint Electronic Engineering Device Engineering Council. And they call themselves JEDEC. JEDEC is just an organization like NEMA, National Electrical Manufacturers Association. Normally what happens, we get a new technology that becomes extremely popular. and everybody's doing it their own way. So when they originally started wiring houses, and we started going to plug-in cord, everybody was doing their own thing. So the electrician would come in here and they'd put a plug in there and they'd put a cord on there, and your plug went bad and you couldn't get them from anybody but the manufacturer. So they turn around and they said, well, we've got to do something about this. So so NEMA was created, which is the joint engineering. So all these companies get into this, and that plug over there is a NEMA 520 plug. It is open technology. Who can make it? Anybody. It mounts in a standard mount. So now I can go down to Lowe's and buy a plug. I can go down to Lowe's and buy a cord, right? You understand? Because these are standards. So on packaging, in electronic packaging, so we started making transistors, and I'm trying to make a company that makes circuit boards. And this guy's got a package that there's no standard mask out there. So I have to get my engineers to come down there and make a mask. Well, if it was a joint mask, if it was an open technology mask, that means odds are I can buy a CAD program like AutoCAD, and that layout with all the spacing and everything would be perfect, and all I got to do on my drawing is just what? Pull it in. So JDEC is the one that registers packages. So that TO3 pack, that's a transistor outline. TO3 is a JDEC register pack. Anybody can make that. So that means no matter what it is, whether it's an integrated circuit or whether it's a bipolar transistor or an SCR, if they put in that package, and I'm a cat and I'm developing a circuit card, I can pull in the mask for a TO3 pack, and I can make the circuit card for those. So instead of me making not only circuit cards and making masks and everything, I can make the part and use a standard package, and then somebody else can make the circuit cards, right? You understand? So I can make the refrigerator and let somebody else worry about the cord. So if I put a NEMA 520 cord on mine, or a 240 cord, and then the electrician can buy a plug that thing fits into. And me as the manufacturer, I don't have to do everything anymore, right? You understand? And it also makes it easier on consumers. So on your transistors, your JDEC registers transistor will always start off on 2N, and then they'll have a number. So we're dealing with a 2N3904. Now the number is just a number that's assigned, so they don't group them in numbers. So that makes sense. So now if it's a JDEC registered package, it's got a number, then odds are I'm gonna be able to look these up. And the 2N3904 is an open technology transistor too. So this was before the days where usually when a science is new, it's not like that anymore. They used to share all of that. Bill Gates screwed that up when he came out with BASIC. Used to all this stuff would float around. It was unbelievable. Y'all know that story, right? And he was going to demonstrate his basic programming language, and he got there, and everybody there already had a copy of it. And it made it mad, so he started registering software. So a 2N3904 is an NPN transistor. And of course, this would be the symbol we use, right? That makes sense. Well, let's say I came over here and do this. So let's come over here and take our AND gate. So here comes my AND gate. And we pull this up. I'm going to use 2 inputs. And I take the output of this and feed it into this circuit right here. And then I take my output off here. We'll put a voltmeter. So I start off, I have 4 inputs, 0, 0, 1, 1, 0, 1, 1, right? I come over here and put a 0. This guy right here will turn on. If we set this to 0 volts, this guy right here will turn off. The output would be a 1. I come over here and go to this. This guy here would be on. If it's on, I still got a 0 right there. This would be off. The output would be a 1. The output would be a 1. Here the 2 inputs do like this. This guy here turns off. This guy here turns off. Now it allows this plus 12 volts to come over here, and it's going to be dropped. Let's say this is plus 5 volts up here. This guy's going to drop 4.3 volts. This guy's going to drop about 0.7. This guy here is going to turn on. The output would go low. This is no longer an AND gate. Because the AND gate, we said, it takes all highs to get a high. This would be a type of gate called a NAND gate. The N means it's got a low active output. And what we say about this, it'd say all highs equal a low. Now what happened is that eventually they said, okay, instead of me having all these diodes and have all these transistors are not providing any power. So instead of me building this as a individual components, why don't we integrate this whole circuit on a single chip? In fact, we got a lot of room in there. Why don't we put multiple circuits on that single chip? And instead of using the symbols for the device, give the circuit a symbol. So they came up with symbols. So they said, okay, this right here would represent and y'all have a problem drawing these. But notice the inside, this is caved in, right, to understand, or concave. These right here are convex. And this guy here could have more. I'm just going to put, this is the symbol for an OR. Now that represents a circuit. Is that TTL? Is that TDL or whatever? No, all OR gates do the same thing. You'll have to understand the makeup on the input to determine what's going to be a high, what's going to be a low. But this guy right here says any high equals a high. And let's write that off. So any input, let's redo that. So we abbreviate this a lot. That was a movie. Y'all Intensity. Y'all read that book or watch that movie? Y'all ever watch that? But there was a girl. Her name was China. And she would pray all the time. She got in trouble all the time. She would pray all the time. And so she finally realized that God knew everything she was going to say. But so he should say, God, this is China alive and well, or something like, this is China doing okay. So we're going to abbreviate this, right? Instead of saying this all the time. Any high equals high output. Of course, what we're going to do is we're going to say, this is the way we're going to say it, any high equals a high. So what we're going to always do on this side, we're going to talk about the inputs. On this, we're going to talk about the outputs. Now, of course, I could come up here and do this. So let's say I come over here and do this. Now, OR gate has to have a minimum of 2 inputs. What do I say about this? Any high equals a high on the output. So OR gate's got to have at least what? 2. How many can it have? Well, I've seen them with 12. That's the biggest one I've ever seen in a chip. And we'll show y'all later on how you can cascade these things and get whatever you want out of them. So normally when we do truth tables and we learn symbols, we learn them with 2 inputs. But you got to understand, an OR gate's got to have a minimum of 2. Everybody understand that? A maximum of a lot. Of course, we're going to put them in standard packs. Well, if I take that and take that OR circuit and run it into this little guy right here, so this guy has a symbol. By the way, this is a type of logic. This would be called DTL. Now, what the first one tells you is what we input on. So the inputs are connected to diodes. This tells us what we output on. So that means this type of logic would input on diodes and output on transistors. That makes sense? DTL. This is obsolete. Of course, this is obsolete, but this is one of the first things they did. And I can still make these gates. Normally, we won't buy DTL logic, but sometimes we actually make DTL logic with actually discrete components. So here, this would be the symbol of that AND gate output. So that would be called DRL, right? Input on diodes, output off a resistor, DRL. So RTL would be what? That's a type of logic. We input on resistors, output on transistors. So this is a symbol for an AND. So notice this is flat. These still concave, but they don't come to a point. So an AND looks like a D, an uppercase D. An OR looks like, I don't know what you say it looks like. So this thing curves. These guys come to a point. See that what I'm talking about? Huh? Kind of like a, but a half a moon, this right here is still curved. An OR is like this, so it literally comes to a point like this. So it's like this. Right? This is the only gate that has a single input and a single output. This is the symbol for an inverter. Now what's nice is that these guys, the logic they perform is the name of the gate. An inverter, the logic they perform is not the name of the gate. This performs a logic we call not logic. But the name of the circuit is an inverter. So this is one of those things. Why did they do that, Rich? Heck, I don't know, but that's the way it is. Now notice what I'm going to do. I'm going to take the symbol for an OR. So this says any high equals a high. Now, of course, the long drawn out would say if all inputs are, if any input is high, that's what I should have wrote. If any input is high, the output would be high. Or we can abbreviate it, right? And say any high equals high, which is the best way to do it. Are you okay? Yes or no? So what would I say about this guy? Well, I'd say all inputs have to be high to equal a high output. I'm going to come over and take the same symbol here. This is the symbol for an OR. And I'm going to put a bubble on the output. This is the symbol for an OR circuit. So y'all should already know the NAND in your head, right? What would I say about this? So if I see this, I'm going to start off with any. There's no bubbles over here, so I'm going to say any high. I'm going to look at the output. If it's got a bubble on there, I'm going to say what? Low. So any high equals low. If any input is high, the output will be low. So guys, what would I say? Here's a NAND. So what would I say? I start off with the term what? All. No bubbles on the input, so I'm going to say what? All highs. I look at the output and says it's going to equal a what? A low. Guys, these are the 5 basic logic gates. This is it. These are the 5 basic logic gates. This is it. All other logic is made from, so we got the 5 basic gates, and then we got something called combinational logic. What do you think combinational logic? That's when we use these 5 gates to do more complex operations. So all our latches, all our flip-flops, all our counters, all our adders, all our subtractors, all our multiplexers, all our decoders, all our encoders are made of these 5 basic gates. So these are the 5 basic gates. What are they? AND, OR, NAND, NOR, and NOT. They're the 5 basic logics. But it's the name of the gate's inverter, but the logic is an AND. I'm sorry. The name of the gate is an inverter, but the logic is a NOT. So now all we got to do is figure out what is a high and what is a low, right? Time's class get over. This class gets over. Huh? I need to help me. I got 9:30 on my head. So.
I'm with you.
Yeah, but I got to leave up. Now, sometimes we teach the class if it's different. If it's a 5 credit hour, it's a 3 credit hour course that we do in a mini term. It's at 9:30 or sometimes even 10. It depends on when you start the class. Yeah, but it's it needs 5 hours a night. It's one of those mini terms. So you get through with the class in 8 weeks. So y'all got any questions so far? Yes or no? No? Yes? So let's we'll give y'all a chart, by the way. I'll print this out. There's a lot to know about this, and we're going to keep adding to this. Just a study guide I'll give y'all out. Say thank you. Thank you. What? Okay, this is digital. This is the 5 basic gates. You answer that.
Yeah.
This is digital. This is digital. The 5 basic gates. And then what we're going to do is we're going to combine this and start. Well, first of all, we'll look at how we would make it with basic gates, and then understand that if it's a circuit that we use over and over and over again, somebody's going to integrate it. Y'all understand that? You know, it's just like central processing units for CPUs. When I first started working on computers, our CPU on our computers, it was a mini computer. It was made of 3 big old cards, had transistors all over. Well, somebody said, "Well, good gracious, why can't we integrate that whole thing on a piece of silicon?" So that's the way we got microprocessors. It has millions of transistors in them, but they're so small. But all they are ands, ors, nots, names, and ors. So everything you see a microprocessor do is done with those 5 basic gates. We can make them, we can come up with circuits to make them add. We can come up with circuits to make them subtract. We can make them encode. We can make them decode. We can make them multiplex. We can make them demultiplex. We can do all kind of digital stuff. We can't do analog stuff. And then that's not true. Then we got what we call digital to analog converter, and we got analog to digital converter. So we can use. We got to go. So somewhere we're going to switch between the two. So a digital analog converter would start off digital, and somehow would have electronic circuits that generates an analog output, equivalent analog output. So these are the 5 basic gates. If you don't understand these guys, then you'll never truly understand digital logic, or how an encoder works, or how a decoder works. And of course, we're going to have to look at the inside just a little bit, not much, just a little bit, so we can understand when it's bad and when it's good. But what's nice about this is you're not troubleshooting a transistor, you're troubleshooting a circuit. So what happens if a transistor blows out? Well, you don't replace that transistor, you replace the what? You replace the integrated circuit. But you need to know what is a legal high, what is a legal low, and all this other kind of stuff you need to troubleshoot this. And you still run into these gates. More and more, though, common circuits are going to be integrated now. So now you look at a microprocessor, and you look at a motherboard, and it's probably got the microprocessor on it. That's still a unit, but it's some of them, we got them in now in the billion transistor range. That's what this guy here is. This is the heat sink. They sink that thing. There's so many transistors in there, even though they're little tiny transistors, and each one of them might be generating, microwatts. You multiply a microwatt times a billion. These guys pump out 45, 75 watts of power just because there's so many dang transistors in there. So we got to get rid of the heat. So normally what we have is we have a microprocessor, or a CPU, or whatever you want to call it, which is it runs programs. People call it the brain. All these guys can do is run programs. Well, I guess that would be right. Okay. And then you have a chip that's responsible for running the motherboard. We call this the chipset. So all the circuit that actually runs the motherboard is in the chipset. And then this is becoming. If you buy a desktop computer, you'll have what we call expansion slots on it, which gives you the ability to do what? Add stuff to it. So that's the big advantage of a desktop over a laptop. A laptop, you get what you buy, right? You understand. A desktop, you can add to it, right? Or take away. So if you don't like the video card that comes embedded in the thing, you can go out and buy your own video card and plug it in there and run what you want to. And of course, this is where the memory goes right here. These are called these are for dual inline memory modules. It goes right here. This is for the power supply. This guy right here is becoming obsolete. This is for a technology called parallel ATA. Just about everything's going to what we call serial ATA. And you can see the difference. This guy right here could handle two drives, two storage devices, like a CD-ROM or a hard drive. Each one of these can only handle one. But look, so 4 of these, which can handle 4, would take up less physical space than this guy here that could only handle what? That could only handle 2. This is the new expansion bus right here. This is called PCI Express. This is the video slot right here. This hasn't changed very much. And the technology of the computers hadn't changed in a long time because there's really no need to change. What's about the only thing they're changing? They're changing processors. They're giving the processors more characteristics or more speed or more capabilities, but the layout of the expansion bus and everything are still the same. If you understood that, there's 2 main makers of microprocessors. Anybody know the 2 guys? Intel and AMD. Yeah, those are the big guys. Now there's still Zilog is still out there, but they've moved into their domain, which is control. But Intel and AMD dominate laptops and motherboards and desktops. Tablets, they could have anything. I think. So what would I say about, what's the name of this gate? And what do we say about it? If I see this symbol right here, if I see this D, I'm going to start off with all. Not low. And we're going to abbreviate that. So the whole phrase would say, if all the inputs are high, the output would be high. That's the phrase, right? You understand? But what we're going to do is like China did on intensity. You ought to watch that movie. It's intense. Let me tell you a little bit about it. It's a guy that works for, get it. Read the book. Read the book. It's a Stephen King. It is a good, if you like scary dramas, you like it. The movie's okay, but the book is good. All highs. So what are we talking about over here? Yeah, what we're doing is we're looking over here, and what we're doing is looking for bubbles. So after a while, we're going to start putting bubbles on the input. But if I see bubbles on the input, I'll start off and say all lows. Okay. So here we have no bubbles on the input, so I'd say all highs. We don't have a bubble on output, and I'll say equals a high. So now if I did a truth table, how many combinations of this I can put? I can put 4. All highs equal a high. So all highs equal a high. What's the rest of them going to be? Well, what's the rest of them going to be? If this is the only combination that gives me a high, what's the rest of them going to be? Y'all understand that? Because this is an any right here. This is the all. We'll talk about that in a minute. This is a what? What's the name of this symbol? 4. What type of logic is this? I don't know. It could be RTL, it could be DTL, it could be ECL, it could be TTL, it could be MOS, it could be anything, right? You understand? But all these different logic families do the same, ORs do the same thing. It's just the electrical characteristics that change. What's a true high? What's a low? How much current can it drive? What can it do for me, right? You understand? Here we'd say, if I see this, I'm going to start off with what? With the term what? Yeah, we're going to say any. We'll look at the inputs. Any high equals a high. So if I see this concave section and these things right here, I'm going to start saying any. Now, if I did the truth table for this, by the way, how many inputs would this apply to? Any high? Is that 2 inputs, or that 3, or 4, or 5, or 6, or 7, or 8, or 9? It's all of them, right? And that's why I worked with a guy one time, and we were working on a digital circuit. And he would go in there and he would write the truth table beside all the gates up there. That's the way he troubleshooted. So instead of learning any high equals a high, he wanted to do truth tables. George, if you know any high equals a high, you don't need a truth table. So if you see that symbol and you understand any high equals a high, you don't need a truth table. So the problem is, this truth table would take 4 combinations. I had one more input. Now I got 8. Right, you understand? I go to 4 inputs, now I got 16 inputs in a truth table. I go to 5 inputs, now I got 32 entries in a truth table. But every one of them is going to be any high equals a high. Well, let's do the truth tables, because truth tables are always on test. By the way, usually on truth tables they use 2 inputs to limit you, because if you know the combination on 4, then you know the combination on 8, right? Is this any high? Is this any high? It takes any high to get a high. Is this any high? Okay, is this any high? Is this any high? Y'all understand? So I can make a truth table from that term. But what I'm saying, if you learn the phrase or the expression, then you don't need truth tables for the basic gates. Now, when you get into the combinational logic gates, there's no phrase. So there's no phrases you're going to learn, right? You understand? But if you understand how to read the truth tables and how to read these tables, then you can figure out how they work. The lab we're going to do tonight is we're going to let y'all inventory y'all's kits. Y'all decide who's going to be your partner. So this logic right here is a NOT. So what we're looking at is what logic does it do. What would I say about this? I'd say high equals a what? No. So we don't say all. This is the only gate that's got one input. Two combinations in a truth table. So this would give me this. High end gives me a low out. So what would a low end give me? High out. There's the truth table. Are we okay? Everybody okay? So this is what you need to start working on. And like I said, what I'll give y'all tonight is there's a lot more to it. For one thing, these guys have a mathematical expression. We call it Boolean algebra. Boolean, B-O-O. I had an instructor call it Boolean. I don't know where he got the G at, but it's B-O-O-L-E-A-N. And there's an algebra for this, and it's a logic. It's not. A lot of the rules that apply to algebra apply to this. But if you got A and A, it don't equal A squared. So we don't have any exponents. We don't have any of that garbage in Boolean. So every gate is given a math expression. And if you can set up an equation for a circuit that you come up in your head, and then the circuit and then the equation reduces, what that means is the size of the circuit just did what? Reduce, which is what's so cool. So it allows you to reduce circuits. So what you can do is you can come up with a circuit in your head. Then if you can develop the Boolean equation for the circuit, then you reduce it. If it reduces down, it really popped into my mind when I was working at U.S. Steel. We bought a scale from Electroscale that didn't put an auto zero on. So what would happen is these trucks would pull on that big old scale, and they would always drop garbage on there. Well, what would happen? The weight would keep rising up. So you'd be sitting looking at the scale, and it'd have 500 pounds on it before a truck pulled on there. Truck drivers don't like to pay for 500 pounds of stuff that's not on their truck. Companies don't like to do that. So normally a big truck scale will have an auto zero on it, which means if it sits there for every once in a while, you just automatically zero the scale out. And then if you come in and you sense motion on the scale, you don't zero. So that way you're constantly, and so they bought that thing without an auto zero on it. So I said, well, I'm going to design one. So I designed one, and I put all this together, and I come up with this big old circuit. And I went into the boss. I said, this circuit right here will work. I checked this out, and it's going to work great. And he said, well, let's see if it will reduce. Oh, great. He wrote that thing out, and he reduced it down, and it was unbelievable what we ended up with. So I had like 15 ICs, well, not circuits, and he dropped that thing down to like 5. And we put that thing on there, and if they still got an electric scale over on the lime scales, it's got my auto zero circuit in it. I don't know if it's in there. It was one I put together. Worked great. So that's what we're talking about. If you can reduce these circuits, you're actually talking about cost, right? You understand? So if I can represent this in math and then reduce that equation, and we're going to look at it. In fact, all the equations that we're going to reduce in this class, that would be more in design. We don't teach design. We teach how they work. So we got a lab on reduction, but I've got it reduced for you. So you'll see, and what's so neat is you're going to wire up one circuit with all these ICs, then you're going to wire up another circuit with half, or we did one where you got like 5 ICs over here, and then you put one. I mean, and it does the same thing. And you'll do a truth table, and it does the same thing, and it'll let you see the power of this and why we do things. So no, we don't teach design, but if you were in design, you'd be learning about Karnoff mounts and Boolean algebra and all that neat stuff. We'll just tell you what the circuit's supposed to do, and thank goodness they've all been designed for us. So we call this a what? If it's got a low active input. That's not true. Let's go ahead and get this. What we do to get the nands and the nors is we look at what we call the active state of the input, and we compare it to the active state of the output. Here the inputs are high active, the output is low active, and that's what we say, so it's low when it's true. If they're the same, up here the inputs are high active and the outputs are low active. So if the inputs and the outputs are the same, that's where you get the ands and the ors. If they're different, that's when you get the nands and the nors. This is going to be coming in very important when we get into what we call negative logic. So right now, notice all the inputs are high active. So we refer to this logic as we call this positive logic. What would I say about this guy? We'll say all highs equals a low. My truth table, I have 4 combinations. Oops. Yeah, nope, I missed one. That's why it's good to know if you know the number of combinations, you know if you skipped over one, right? So what would I have here? Well, I'll just go over here. I'm going to go down here and put this. That's the only all, right? You understand? And what would I put here? See how easy these, if you understand those statements, how easy developing the truth table are. And of course, on tests, you're going to identify truth tables. Because when you look at the data sheets are not going to give you the stuff right here. Data sheets are going to give you highs and lows. They're going to give you a truth table. And what do we call this? And what we say here. If I see this, I'll start off with what? Any high equal low. Are we okay? Yes, no? And of course, the truth table. So is this any high? Is this any high? Is this any high? Is this any high? Now, a lot of people say, and later on, notice we only have one combination here that gives us a 1. Then all the other combinations gives us 0. So what would I say about this guy? If I was going to come up with this phrase right here, what would I say about this guy? I would say all lows equal a high. Yeah, is that true? So if I have all lows, I get a high. Any high, I get a low. Y'all see that? So what would the symbol be for this guy? All lows equal a high. Well, it's called a NAND. Why is it called a NAND? I did not make it up. Why is it called a NAND? Because the active state is low, the input active state is low, and the output active state is high. So what I'm trying to tell you, don't jump on the bubble on the output as being a NAND and an OR. This is called a negative NAND. So, we'll talk about these later. So don't say, well, if it's got a bubble on the output, it's a NAND and an OR, right? You understand, or not, it's going to screw you up. Because later on, so what we're going to find out that your 5 basic logic gate actually has 2 symbols. So we have 10 symbols for 5 gates. We got 5 negative logic symbols, and we have 5 positive logic symbols. And when we start looking at schematics, this is really going to make sense. Why did they do that? Right now we'll work on these. So when I give you the handout, we're going to be working on positive logic symbols right now, and then we'll look at negative logic symbols later, but it's still going to be in the handout. All right? You understand that? So basically, and what we're going to learn is you have 5 basic gates. Each one of them has 2 symbols. So that gives us 10 symbols to work with, and if you understand those symbols and what those symbols are trying to tell you, then you're going to be okay in this. Okay, I'll take a break and we'll look at one thing we're going to be doing on lab. Talk about that. We'll split up and look at our first lab. Got 2 more things we need to talk about. And we'll talk a little bit about this, and we're going to have to kind of understand it. Everybody okay here? Like I said, I'm going to give you a handout with this information on there. But not only is it going to have the gates, it's going to have the expression, it's going to give you the gates, it's also going to give you the Boolean equation for the gate, and also it'll give you no truth tables. Because if you understand this, this applies to all versions of this gate, whether it's 2 input or whether it's 10 input, right? You understand? Couldn't you imagine making a truth table for a 10 input OR gate? It would have 1,024 combinations in there. I'm on page 51 in the textbook. And we'll learn a little bit as we go along. But this is a standard TTL gate. 51, I'm sorry. And we'll learn a bit more about it as we move along. But I'm going to show you why they call it a TTL gate. They call it a TTL gate because we input on transistors and output on transistors. So that's how it got its name. And this is this right here. We have a resistor right here. These all connect together, and I can't put the power up there. And normally we put a diode right here to prevent us from putting a negative input on the gate. So it would clip a negative input off. So this guy in the front is just for protection. So it does nothing. This is a TTL inverter. Now, every time we get one of these, wouldn't it be awful if I had to draw that whole circuit out? But what happens is this symbol represents that circuit. That circuit right there somehow gives me, when the input's high, the output goes low. But this guy right here, we call this the totem pole output. This guy right here provides both. When it's output, this guy turns on and this guy's off. When we output a 0, this guy turns on and that guy turns off. And we'll show y'all a little bit as we go along how this works. But it's not really important to understand what circuit's in there. What's important to know what? A high gives me a low. If it does not give you that, you don't go in there and replace Q1. You replace the what? The IC. But what we have to do is look at this so I can understand what's a legal high and what's a legal low. TTL operates on plus 5 volts. So in logic, in semiconductors, the term VCC means if we connect power to the collector, you can see that's called VCC. In solid state, that can be anything. In digital, if you see VCC, they're talking about plus 5 volts. Now, the limitations on this, but you have to understand it's impossible to get exactly plus 5 volts. Even with regulators, there's no such thing as a perfect voltage regulator. So that means when you load these power supplies, the voltage goes down a little bit. When you unload them, they go up a little bit, but it's not very much. So this is actually plus or minus 5%, which would be anywhere. So if my power supply was between 0.75 and 5.25, that would be great. Okay. Now, what's a high? This is positive logic, so we would think plus 5 would be high. But if I put plus 5 volts as my power, I'm never going to get plus 5 volts out. So we can't say plus 5 volts. We know it's going to be less than that. And we're dealing with a lot of circuits, right? You understand that? So what does that mean? Well, we're going to get a range of voltages that's going to be a legal, what we call a legal high. In TTL, a legal high is anything above 2.4 volts and less than 7, but we never see it. We'll talk about later on. And we'll see how we actually get there. So 2.4 volts and up, this right here would be what we call a legal high. So what's a legal low? Well, I'm not going to put 2.4 volts because it might not be 2.4 volts. It might be 2.6 volts. It might be 2.10. So, but we're trying to get it as close to ground or 0 volts as we possibly can. So what we're trying to do is anything less than 400 millivolts is considered to be a legal low. And anything between here, this is invalid. Now, why do you need to know that? Because if you look into a circuit and you see 2 volts, you say, well, that's a high. Well, you done screwed up because that's in the invalid range. Now, invalid means there's no guarantee that the gate will accept it as a high. It's going to accept it as something. Y'all understand that? But is it going to accept it as a high or is it going to accept it as a low? These outputs right here are going to, these guys out here are either going to be switched on or they're going to be switched off. When this one's off, this one's on. When this one's on, that one's off. And they're going to switch. They're never going to be on at the same time. So if I put 2 volts on the input, is it going to be a high output or is it going to be low output? We don't know because it's invalid. So anything above 400 millivolts in TTL is considered to be a legal what? Low. Anything above 2.4 volts is considered to be a legal high. If I get into a circuit and it doesn't have those ranges for lows and highs, then I would start trying to figure out, you know, it might work now, but it might not work tomorrow. It might work in the summertime, but it might not work in the wintertime. We had a scale down in a plant down in Columbiana. They made railroad wheels down there. I don't even know if it's still down there. But they had a scale in the wintertime. It would stop working. And of course, we would go out there. We came in at 8. We'd get up, got our truck loaded up. We were up in Pelham. Got our scale truck loaded up. We'd haul down there. We'd get down there at 9 or 9:30 and the thing would work great all day long. Then at night, when it was cold, it would stop working. That was fun to fix. Didn't like cold weather. The problem is the shed that the scale unit was in was outside. It wasn't heated or anything, and it didn't like cold weather. Of course, we finally figured out what was wrong with it. So, but the problem is that they depended on this guy right here. They depended on something to be accepted as a high. Well, what happened in the cold weather, it got down in that invalid range. Can you see why it's called TTL? Because we input on what? A transistor, and we output on transistor. So this is called transistor logic. So I got two ways I could figure out if it's a legal high or legal low. I could get a meter and put it on in there, right? The problem with digital meters is they're analog to digital, and they have to go through a conversion. So it's kind of like binary. You know, you're going from decimal to binary. Do you do that instantaneously? No, it takes time. So your meter has to go through a analog to digital converter. So one big advantage of digital meters is they don't work well on something that's changing. They'll be all over the place because they're trying to convert it over, and it changes before they get it converted. Especially DC guys. So it'd be nice, and oscilloscope's really good because the oscilloscope shows you what's there. It don't go through an A to D or anything like that. It shows you what's there, right? But another tool we have for very slow moving signals is something that we call a digital logic. And these things are not very expensive. They don't work well with fast changing signals, but if you got static signals or slow changing signals, these guys right here work great. Oh, this is the wrong thing. Let me have one that's got LEDs on. Yeah. We have two types of logic out there. And when you get your probe, if this thing will focus in, notice it says DTL. This is an old one. This is diode transistor logic. You're not going to run that. We just looked at diode transistor logic, right? And then TTL. And then another type of logic called CMOS. So we're going to be working primarily with TTL. So we'll make sure this is on TTL because that's what the probe uses to determine what's a legal high and what's a legal low. And then normally these things have a switch on here called pulse and memory. So memory would be, you'd use that to capture a pulse that comes every once in a while. Normally we'll leave it on pulse. And then you got two LEDs on here. One of them's called a what? High and low. Give it back. High and low. Now these guys here look for legal TTL levels. Because if it's invalid, both the lights will be off. If it sees a legal high, then the red light, this high light would come on. If it sees a legal low, then on this one the green light would come on. If neither light's on, what does that mean? That means it's invalid. So these are nice little tools. Okay. If you got a pulse stream, these lights can blink a lot faster than you could ever see. So if I've got a light that blinks extremely fast, what does our eyes do? These lights right here are blinking 120 times a second. They are literally turning off 120 times a second. You have two zeros in an alternation. They are turning off 120 times a second. What does our eyes look like? So this is why shirts look different colors out in the sun than they do inside. This is why when you snap a camera under here, it turns out yellow. Because your camera sees the lights that's there, our eyes blends all this together, so we actually see more light than actually see. So what happens is that if this thing sees a square wave that's moving too fast, then both your high and low lights are going to come on. Which means I'm seeing a string of highs and lows. If your high light is on more than your low light, it means it's staying high a lot more times than it's low. We need to talk about another thing too. It's very, very important. And of course, if your low light is brighter than your high light, it means it's staying low. The pulse is staying low longer than it's high. If you're sitting here and this light flashes so fast that you can't see it, so we got the probe in there and it gets a little pulse, the light turns on, but my eyes don't see it, then what happens is this pulse light goes to a circuit we call a one-shot, which means if it ever sees a change in state, the light will blink. You won't see the high light blink, and you won't see the low light. So if it's staying high all the time, and you see that pulse light blink, it means the low light turned on, but you didn't what? It was so fast you didn't see it. So, but the pulse goes through what we call a one-shot, which gives us a certain amount of time, no matter what the pulse is. So if you see a clock, all three of these are going to be on. If it's staying high all the time and you see this light right here blink at you, it means it saw what? It saw a negative going pulse. If it's staying low all the time and you see the pulse light blink, it means it's got a positive. These guys right here have no batteries in them. What do you think these are for? You power this sucker off the circuit under test. So if you go and get this and come over and start probing around in there, it means nothing, right? So you power this off on the circuit on the test. What are you going to put the red lead to? Positive. What are you going to put the black lead to? Negative. So these guys work off DC. And they're really neat. They're cheap. They don't show you exactly what's there, but they give you a good indication of what's there. If you want to see exactly what's there, then you're going to have to get you a what? You're going to have to get you a subsystem. Or you might have to get you a device called a logic analyzer. I'll pull that thing out and show you that. The problem with these, how many signals can I look at with this at any one time? What if I'm trying to see all highs to get a low, and I've got a 30 input AND gate, or a 16 input AND gate? Well, a scope's not going to do any good because I can only look at two things at the same time. So we'll show y'all a logic analyzer, which gives us the ability. We've got one that can look at, we got some that looks at can look at 32 input signals at the same time, which is really neat. So we'll show you some of the more expensive test equipment. I think we got a combination of a digital scope logic analyzer. It's a really neat unit, and I think it was priced at used. It was like $100,000. We got some more that's cheaper. I can't remember what we gave for them, but and we'll show y'all both these. So what we're going to do in our lab is we're going to, and I'll give you the labs out, right? We're going to inventory our lab kits. So y'all, your team, we're going to work in teams of two, so somebody's going to have to work by themselves. Everybody's here, right? Huh? Yeah, we are. So y'all pair up so when he shows up, he'll work by himself. So what we're going to do is inventory the parts. So let me show y'all this first. So we come up here, we put packages. And these packages are JDEC registered. And the packages we're going to deal with is what we call a dip. Now, we're going to pass these around. These are TTL, so they're not static states. We don't have to worry about static. So these are what dips look like. Oops, wrong thing. I closed my camera out. Dang. And we've already talked about that term already, right? We did that this time. About a dip. Yes or no? So this is a package called a dip. Dip. It's an acronym. Y'all know what an acronym is, right? What's an acronym? What's an acronym? It's when we take a phrase, we not abbreviation. It's not even abbreviation. Then we come in and we use the first letter. So this stands for dual inline package. It's not abbreviation. It'd be more like a mnemonic than anything else. But the acronym is we take the first letter off pertinent words. So usually we drop ofs and these unless they make sense. Then we come down and we bring this down and we use this to create another word. That's a true acronym. Now over time, we basically say the letters now, we call them acronyms. Like SEC, this is sick. Most people don't say sick, they say what? SEC. Well, SEC is an acronym, but if I did the word, it would be what? Sick, right? The first acronym we looked at was ASCII. ASCII stands for American Standard Code for Information Interchange. Well, notice the F's not in there because it didn't make a word, right? So sometimes they drop letters. So dual inline package, or we call them DIPs. Okay? So a way a DIP starts out, and these guys got all the way up to 64 pins. Is that when you look at them from the top, you're going to see a lot. We call them pins for obvious reasons. They'll stick in you. Those are supposed to be lined up. 1, 2, 3, 4, 5, 6, 7. What we're going to pass around now, this is what we call a 14-pin DIP. And acronyms are supposed to be, by the way, acronyms are supposed to be given in all uppercase. They'll do that. So we call this a 14-pin DIP. Now, if you look at it from the top, and when we look at it when you get on the bottom, everything flips over. But when you look at it at the top, there's going to be a notch in one side, or there's going to be a dot on one side, or there's going to be something that identifies the top of the chip. Now what we start doing is we start numbering on the left, 1, 2, 3, 4, 5, 6, 7. Then we come around and number up. 8, 9, 10, 11, 12, 13, 14. So 1 and 14 are beside each other. So what you're looking at is you're looking at a 14-pin DIP. There's a picture of it on page 51. And the spacing is critical, and we'll show y'all some 24-pin DIPs. They got bigger, then all the way up to 64 pins. The biggest thing I ever seen was in a DIP package was a Motorola processor, 68. What was that? But it was a 64-pin DIP. Then they realized they could get more pins out coming out the side, all 4 sides, so they started going to squares. Then what they do, then we have what we call the pin out. So the pin out shows us what's assigned to each pin number. So I'm going to come over here and I'm going to do this. And that would be that whole circle. So I've got 14 pins to work with. An inverter needs 2 pins. So how many can I put them in there? We put 6 of them, right? Because people keep forgetting we got to power this thing up. But all these circuits are inside there, so they share the same power pins. This is common. And this is VCC. What's VCC on TTL? What's VCC? How much? What's the value? VCC? What's the voltage value of VCC? Voltage value of VCC? Plus 5 volts. Plus or minus 5%. These are commercial grades. Now what they do is they sign this a number. Okay, you okay? So undoubtedly we're not learning very much because we just got to start talking about what VCC was just a few minutes ago, right? So this is the pinout. So what does the pinout do? Well, it shows us what's assigned to each pin number. So there's 6 of these guys in there. The only thing they have in common is they share the same power pins and they're in the same package. So you're looking at a 14-pin dip. I gave this.
Oh, you want to take?
No, I want y'all to take one. I want you to hold these suckers in your hand. I'm sorry. I guess I should have told y'all. So can you see, when you get yours, can you see the little identifying notch on there looking at it from the top? So the first pin on the left is pin 1. Then it would come down the left-hand side, go over, and come up. No matter how many pins are on the dip, this sequence of numbering is the same thing. So if I had, and they go in 2, so there's no, so you got a 14-pin dip. So the next one would be a what? A 16-pin, because they got to, it's a dual in line, right? Then an 18, then a 20, then a 22, 24. When they got to 24, they had to do something different. They made the package wider. But the way we set up the pin numbers are exactly the same. First of all, you identify the pin 1 side, right? It's either going to be a notch or it's going to be a little nipple in, right beside pin 1. Then you do what? You start counting down, you come up, and go down. So if I was going to wire this circuit right here, for some reason, how would I wire it? Well, the first thing I'm going to do is I'm going to look at my package, and I'm going to assign pins. I'm going to come over and I'm going to say, what? 1. What would be the, if this is the input, what would be the output? Pin what? Okay, guys, if you got your book, look on page 51. If you can't see this, this is the pin out right here. This is a 7404. Which we call, this is referred to as a hex inverter. Can y'all see why? Why is it called a hex inverter? Because it's got 6 of them in there, right? Hex stands for 6. Okay, so if this is pin 1, this right here would be what? Here's the symbol right there. Okay, it'd be pin 2. Now, how would I get from pin 2 to pin 3? Well, this would probably be pin 3. So out here, I'm gonna have to run a wire out there, right? You understand? They're not connected inside. The only thing they have in common is they're in the same package. It don't, just because you see them hooked up together, you have to make the connection between circuits. If this is 3, this right here would be what? 4. And then of course the obvious and this right here would probably be what? 5 and 6. But what would I have to do here? I would have to jump what? 4 and 5. And then I would bring my input into pin 1 and I would take my output off of pin 6. And I still got 3 more in there to play around with. And somebody's going to do this in this class. Or somebody's going to say, you're going to hook up a circuit like this, and you say, Rich, I've only got 1 inverter in here, And what you're going to try to do is you're going to try to put one IC per symbol, right? You understand? When you got how many in there? You got 6, right? That would be like opening up a notebook and writing on one piece of paper, and you say, well, I need another big piece of paper. Let me get me another notebook, right? You understand? You use all of them in there. So this is called a hex inverter. Why is it called a hex inverter? Because there's 6 of them in there. But I guarantee I'm going to put on the test, I'm going to say, you know, how many inverters can I get in a 16-pin pack? And somebody's going to say 8. They're going to forget about what? You got to have what? You got to have power, and you got to have comm. You got to have power. You can't, these guys here don't work off nothing. So we sacrificed 2 pins, but look at the size of that thing. And that circuit that we drew a while ago, so each one of them's got, let's see, it's got an input, got a steering, got 2 out. So each one of them takes 4 transistors. There's 8 of them in here, so there's 32 transistors on a chip that's, the package is a lot bigger than the chip because they got to make the package big enough so who can handle it? You ever see some of the special tools they got to handle some of these little surface mount things? They got these little tools, got little suction cups on them, and they go over there and pick them up and place them down. These originally, when they came out, they were big enough for us to have. It's just like fiber optics. You get into fiber optics, the conductors in there are smaller than a human hair. So they got to make it big enough for us to handle them, right? So this is what we call a 14-pin dip. These are the first guys we're going to deal with are these inverters. So how are we going to wire these up? Well, we're going to use what we call a breadboard. What we call it? A breadboard. Some people call them protoboards. Have y'all been introduced to the trainer? Yeah, this is an analog and a digital frame. So in this class, we're going to use it to watch. Yeah. So what we're going to use the digital components of the trainer. The lab does a pretty good job, but in fact, the lab covers a trainer that only had digital. This is both an analog digital trainer. So here's our trainer. So we call this a breadboard. There's actually 2 of them. You know how the breadboard works, right? You know there is a break between here and there. So where do you think these ICs go? Well, the IC, so the ICs are going to go across this trough right here. You know, see that? See the trough right here? So everything on this is connected together. Everything down here is connected together. But it don't make a connection to the trough. Why is the trough in there? Well, the trough's in there so I can come up here and I can put these ICs. Okay. Now all these pins up here, all these holes up here belong to pin 1. All these holes up here belong to pin 2. You know, see what I'm talking about? Yeah, we call these pins for obvious reasons. By George, these suckers are sticky. So I don't want to ever come over to your desk and find these things on the table with these pins facing up. Y'all understand why? I'm not going to tell you how many of these things I pulled out of my elbow. And it's not fun. For people that did what? They put them like these. So any ICs that's not being used, you need to keep them inside your parts kit. Make sure you know where pin 1 is when you start wiring these things up. We're going to show y'all some. Make sure you know where pin 1's at. We get people that just come in here and they start wiring. They just hook the stuff up to a pin. Well, it's where, on these, that's where the notch is at. Y'all can't see it. So pin 1 would be right here, right? So we find the notch. This would be pin 1, right? This would go 1, 2, 3, 4, 5, 6, 7. Then over here would be what? 8, 9, 10, 11, 12, 13, 14. Y'all understand that? Yes or no? And of course, here's our 5-volt supply. So we're not going to use the variable supplies in this lab. We're going to use the 5-volt supply. This right here is what? That's common. Okay. Are we okay? We're going to use the generators a little bit. Here's our digital logic switches right here. So we're going to be using these a lot. We have 8 of them. So notice right here on the left-hand side, it's got high, low. So this will give me a 1. This right here will give me a 0, right? Here's the little breadboards that we use to wire those up with. We call these breadboards. Some people call them proto boards, but these are where we actually. Breadboards are very, very popular when I develop circuits. Because what can I do with these things? I can put different parts in here. I can pop them out. I can put them in. I can move stuff around. If I don't like that wire here, I rearrange it. I can pop another IC in here and do that kind of stuff, right? You understand? And once I've got all the bugs out of here, and everything works like it wants, then I wouldn't sell my breadboard. I would do what? I would take those schematics and have a circuit. Well, we have 2 of these. So we can make a really big circuit on these, right? So I've got all this space right here to make these things. So, no, these things are not common this way. So I could take another IC and put it right up against this one, right? You understand? And then I've got this right here. By the way, y'all understand these power buses right here? So what we can do is we can hook up 5 volts to like the red. We can hook up our ground or common to this. Then normally what we would probably do is put one side on it. Since the power is on pin 14, I would probably put my power on this red. Then I would, and since my ground is on pin 7, we would probably put our ground wire here. And then all we have to do for every chip is just jump up here instead of trying to run, and people don't understand that either. If you ever go look at a power supply, or if you ever go look at your house, and if you take the panel off and you looked at the number of wires coming into your circuit breaker, how many comes into your circuit breaker? How many wires come into your circuit breaker? Huh? Well, that's the back of your circuit breaker. I mean, how many wires do you plug into that thing? You plug in 1. You might have 15 plugs out there, but you plug in 1. Well, where did all those hots and neutrals come from? Well, they're jumped out at the circuit, right? So I don't want to come over here and see 15 wires hooked up to the positive, up to the plus 5 volts. We have people that see that. They say, okay, it goes to plus 5 volts. Then I got to run it back to that stop that says plus 5 volts, and not realize they got plus 5 volts sitting 2 inches from, or 2 or 3 millimeters from where they're running. So what you do is you do all your jumping out in the circuit. It irks me in motor controls because we're using little banana plugs, and they'll have 15 plugs. They'll have 15 of those things on the transformer, banana plugs mounted vertical on the bottom of the transformer. And you touch them and they do what? They fall out. So normally on your power source, how many wires do you have? You have 1. Right? And then what? Then you do all your jumping where? So that's what you do on your plugs. You go from plug to plug to plug to plug. Right? Y'all understand that? These are LEDs. These are not LEDs. They're light circuits. So there's actually more electronics. And as the time goes by, we're going to start looking at the schematics on this trainer. So these LEDs, they come on when I see a high, they see a high, and they go off when I see a what? A low. So they're kind of like a logic probe, but they don't look for legal limits. So this, we're going to get the inputs to our circuit from where? We're going to get the inputs to our circuit from the switches, and then we're probably going to hook the outputs over here. So that means I can see all highs to get a low, right? So I can have a 2 input AND gate. Then I'll come up here, I'll flip these switches, and if the light comes on, then I'll go through the truth table. Okay, y'all understand that? So here's our trainer. We're not going to use anything right here. We're going to use the breadboard. We're going to use these logic switches, and we're going to use these lights, these LEDs. So we're going to use the LEDs normally on our outputs, right? You understand? We're going to use what? and then the switches will be on it. These 5-volt supplies right here are very unforgiving. They get shorted out, it'll pop the regulator. So that means before you turn on any circuit that you've got wired, I'm going to come over there and check the power. I'm not going to check the circuit, I'm going to check the power. And I'm going to initial saying that the power's okay. Then you're going to fire the circuit up. So just because I check the power's okay, does that mean your circuit is built right? No. It just means I don't have a short. So you're supposed to know, okay, I've got an AND gate. I'm supposed to have all highs to get a high. If you don't give me all highs to get a high, then either the gate's bad or I've got it wired up. Okay? We don't tear circuits down here and rebuild them, because what you miss out is that you miss out on a perfect opportunity to try to troubleshoot. What you'll find out is that it might take you 30 minutes to build a circuit. It takes you 15 seconds to troubleshoot. So that means if you tore it all the way down and put it back together, you're going to be tearing circuits down and building circuits back up all together. Don't be upset if I come over there and I call the whole class over to see what you've done. You don't understand that, because it's a perfect lot. It's a perfect learning opportunity for the class. And y'all going to make mistakes here, but as long as power's okay, then you're not going to hurt the chip. You'll understand that. And I'll make sure you're using pin 1 and pin 7, pin 1 and pin 14 for this chip. Now, don't take for granted that pin 1 and pin 14 is on. So don't take for granted that the upper pin on the right is power and the lower pin on the left is ground. Because as soon as you think that, we're going to skip where they're not. So that's why we need to look at what we call the pin out. So y'all understand what the pin out is. What's the pin out? It shows us what each pin is assigned to. Right? You understand? So the first thing you're going to do is, if you look back here, so let's go back, if you got your book, if you don't, find somebody to look on with. So no, we're going to go all the way back here to the back. Now we don't understand some of these symbols yet, so I'm on page 394. 934. 934. Oh crap! I just broke the tape. My homemade document camera. But if I come back and look, notice normally when we designate devices on a schematic, we try to do it with one letter. So we have integrated circuit, we could use IC, but IC is two letters. So I can't use I because I is assigned to other devices, C is assigned. So what they start doing is they start using the other letters. So normally integrated circuits are designated with a U. Some people use IC. So this is U4. Okay? Y'all understand? Now, this is combinational logic. We're not going to get on that. But right up here, this is an inverter. So here's U1. You'll see where I'm at? Here's U1. Well, how can this be U1 and this be U1? Well, if you look at the pins, one of them's using pin 5 and 6. The other is using pin 9 and 8. So they're just inside the same chip. Now, some guys don't do this, but this guy here does it, and we'll show y'all later on. Notice one of them's called U1:C, and the other one's called U1:D. So some guys, sometimes they give the individual gates letters. Like they'll start, pin 1 would be A, the next coming down would be A, B, C, D, E. Y'all understand that, how they would do that? But look what they do. They put the pin numbers. So that means I don't have to figure out what pin number they use. They put the pin number on the schematic. Right? You understand? So if I was troubleshooting and I wanted to look and see what's going on here, first of all, I'd find silk screen on the board U1, and then I would count down and find what? Pin 9. and then I would look at it with whatever piece of test equipment I had. But if they just called this pin 1D, that wouldn't mean anything. So when you wire up a circuit, what do you think the first thing you're going to do? Well, the first thing you're going to do is take the schematic and you're going to assign pin numbers. Because what's going to happen is you're going to be going between a data sheet and a circuit, and a data sheet and a circuit. If you take the data sheet and you and your partner do this, and you assign pin numbers, then when you wire it up, then the one person's saying, where do I need to hook this up? Hook it up to pin 4, right? And you're looking on a schematic. So this is the kind of stuff I want to see. I want to see what? I want to see these pin numbers on the schematic before you wire them. Does that make sense? And then once you got them on the schematic, then it makes it real hard, real easy to do what? To wire it up. So now you're not going between two documents trying to figure it. You're going to one document, right? Y'all understand that? So first thing you're going to do, and that's on the procedures, is assign pins. So let me tell you about the first lab. So the first lab we're going to do what? What I tell you what it's going to be? We're going to inventory the part kit, and that's going to be fun because all these things are in a drawer. We got every chip in there that we're going to be using the semester. So what you're going to do, and then let me explain the pin numbers a little bit to you. I'm sorry, the part numbers. So when they originally came out with them, they all JDEC registered. So what they did, and we can erase it. What they did is they started out numbering them. So normally, this is not always true, but normally if you see 74, it means it's TTL. Now that's changed, and we'll talk about, we got some weird ones that came out. They'll start off with a couple of letters. These are manufacturer designators. So SN would be Texas Instrument. Then what they'll do is they'll 74, and then we have numbers. We can have up to 3 numbers up. So we're dealing with a 7404. Now, a 7404 is a TT standard. This was the standard series. Then they started figuring out things. They said, okay, what if we don't need the speed of a 7404? What if we want to make it consume less power and operate at a slower speed? So that means if I wanted to power it with batteries. So they came out with another version. It still has exactly the same pin out. It still has exactly the same number of circuits in there. The pin out's the same, but it runs at a slower speed. So they said, okay, what we'll do is we'll call this a 74L04. So what we find out is we end up with these designators in the center of the number now that gives us the speed and the power characteristics of the chip. If I needed the pin out, I could look up any 7404 and the pin out would be the same. But if I wanted to figure out what was a true high, what was a true low, how much it could output, then I would have to take in consideration these center letters. So the ones we're dealing with is a 74LS04. Where would you find the pin out at? Well, if I got my digital book, I could open it up and look inside the front cover, and I could find a 7404. Third one from the top. So these are pin outs, right? You understand? Is that a 7404? Is that a 74LS04? Is that a 74ALS04? Is it a 74HC04? A 74C04? If they're all the pin outs the same. When those middle letters does not change what it does, what type of gate it is and how it's wired. All it changes is what the power characteristics of the thing. And we got tons of them, guys. We got LS, we got 74H, which is obsolete, 74H, but you still might run into them. We got 74Ls, which we still might run into them. We got 74LS, which is predominantly what ours are. We have 74ALS. We have 74 HCs. We're going to run into these. This is where things get kind of weird. It still has the same pin out, right? You understand? So if I've got a 74HC04 and I needed the pin out, I would look up a 7404. And what's a 7404? A 7404 is a hex inverter. Now, if I wanted to see what was a legal high and what was a legal low, then I would get a data sheet, and I would not use the data sheet for a 7404 for a 74L04, right? You understand? So this is where the power comes into play. So we'd look up a 74L04 or a 74L07. So our predominant ones here is this guy right here. This is the predominant guy right here, LS. So if you look at the top of your chip, look at the top of your chip. Somewhere on there, it has got the part number. Sometimes you have to bend it a little bit. You might need to get you a magnifying glass. So you might see like a DM or you might see an SN. These are manufacturer codes. That mean nothing. By the way, these are open standards. So that means if I got a DM7404, which is made by National Semiconductor, if I went to an SN7404, it would be exactly the same chip, have the same pin out, have the same characteristics. So these really don't mean anything. Then you should have the number, right? You understand? And you probably see a little LS on there. And then you should see an 04. And then you might have a little designator out here, which really means nothing. So here's the part number right here. Then down here you might have another number, but it don't have any characters on it. It might have like a 9603. What it means is this chip was made in 1996 on the 3rd week. So that's the manufacturer code. So what they use those, and then they might have like an A or a C, so they know what machine it was ran on. So that way, if they have a bunch start failing, then they can trace it back to a machine, and they can trace it back to a week, and they can say, oh, Billfold was running the machine that week, right? So they can trace it back or try to figure out what happens when they start getting failure. So can y'all see the number on there? P don't mean anything for us. It's probably a machine, or it might be a version, or it might be something like that. But to us right now, those other numbers don't mean anything. So the only thing that really means to us is this guy right here, and it's going to start off with what? 74, right? If it don't start off with 74 on our TTL, that's not the part number. Y'all understand that? Somewhere on there is going to be a 74. Then it's going to have some letters, maybe or maybe not. You're probably not going to get. We got some of these here. These things we can still find. The 74LS wiped out this guy, and it wiped out this guy. So we'll find out the LS has really good features, and this is the predominant IC. So it took care of this guy. So this guy's not around much anymore, and the L series is not around much anymore. So just about all our ICs will be an LS. But we're going to deal with some HCs, and we'll learn out what this means before long. And what we're going to do when we get into lab 2 is we're going to hook this up and see what this guy sees as a high and what this guy sees as a high, and they're not going to be the same, but it's still going to be the legal level. So what's a legal high? 2.4, anything above 2.4. What's a legal low? Anything below 400 millivolts. So that means if you got a gate that switches somewhere in the center, it's going to switch somewhere in the center, right? You understand? So the HC is going to switch a little different than these guys right here, and they're going to give you a little different switching. So what are we going to need? So let me give y'all at the lab.
Okay, Rick, what